because I hear my voice.
Could be me.
Nobody.
I hear you loud and clear.
Yeah, I hear myself. Somebody has the audio on, so I hear my voice.
Okay.
Who is it? Let me see here. Anyway, I think we.
You can mute all the participants if you are the host.
I'm trying to. Why can I mute all of them? One by one. No, pounds.
Go to
Now,
options.
yeah, okay. Now it's better. I have muted one, and now it's okay. Somebody else is talking now. Okay. I think we can start. We have just. Who was with the music? Okay, now we're fine. So I think we can start because we have only 1 hour and a half. We will make this will be the first of many webinars that we will have in the next month. The main goal is to show you all the new features that we have developed because now Ixcube has really a lot of things to learn, and clearly it's quite difficult with this pandemic problem. It's very difficult to meet. Today we will talk about Falco for Rhino. Falco for Rhino is a new application that we have developed, and the main goal is to simplify. The main goal is to simplify the work for people that don't have a deep knowledge of Ixcube. So chat.
नहीं आ रही आवाज इसे म्यूट करने के बाद आवाज आना बंद हो जाती है हाँ हम तो ऐसे ही करते हैं क्यों आपका नहीं हो रहा है पता नहीं ऑप्शन तो वही वैसे नहीं
Jerry, I think so. Manorama, okay. Yeah, she's shut. Thank you.
Okay. I don't find the option to mute everybody. One by one, I have to click. No. Anyway, okay. So I was saying, Falco for Ixcube. So we will give a demonstration of this Falco today and see how it works. Basically, you see my screen. Do you see my screen?
Yes.
Yes.
I know, sono tutti. Okay. Fine. One thing that you must understand when we are running Falco, Falco communicates with Ixcube in a server client fashion. So Falco is a plugin of Rhino and communicates with Rhino and then communicates with Ixcube with the server protocol. What does this mean? It means that the database and the model that we're working on is inside the Ixcube server, okay? And we are doing everything from inside Rhino. This is very important to understand because the main rule when we start using Falco, we have to use a command connect to server. If we don't connect to the server, clearly Falco is not able to do anything because he just passes all the tools, all the commands, and all the requests to Ixcube. Okay, so this is important. One thing to understand. Another thing very important here is how Falco works. The main concept behind this program is we do not apply properties to objects. I think you use it in any software, structural analysis software, or even form finding software. that we select, for example, lines, surfaces, or whatever it is, and we apply properties to these objects, like the cross section, the material, and so on. Falco doesn't do that. We apply properties to layers. Okay, so basically we have a node property. A node property is a property that we use to define the constraints of nodes, if they're fixed or they're free. Then we have curve properties, okay? And curve properties, we apply them to curves, to lines, NURBs, and whatever it is. And then we have surface properties, and we apply them to the surface, clearly. At the end, we have loads, and even the loads are applied on layers. Okay. Now, why we do this? Well, Falco has in mind the parametric environment of Rhino. And Rhino, I don't know if you know that Rhino is extended with Grasshopper, where basically we can model in a parametric fashion almost anything. There are a huge amount of libraries out there where it's very easy to define very complex models, and with very small effort, we are able to do quite complex things. But there is a problem when it comes to make, let's say, finite element models. You know what we mean with finite element models? We have to, it's not only drawing a few lines, we have to split the lines at intersection points. We have to mesh the surfaces into, so they are connected to the finite elements. It's a huge amount of work going from a CAD model to a finite element model. And here Falco helps us because he does all the work for us. So we just draw a very simple surface normally, and Falco will convert this model into a finite element model. The nice thing is, once we apply the properties to the layers, clearly we don't need to apply properties to the objects. We just have to fill the layers with the objects that we want, and the properties are assigned automatically from the layer attributes. Okay, we will see this just in a few seconds. These are a few examples of meshing. So basically, we don't need, you see here, these are just lines on the top left. These lines have not been split at intersection points, and even the mesh, this is a surface, has not been split over the lines. Falco has done all this in an automatic fashion. Even if you look at the bottom right, where we see this small building, this pavilion here, if you want to make this model as a finite element model, clearly we have to split these lines at intersection points and do all that job there, and then we could define the properties of this. And the nice thing is here we do not have to do that. Okay. So this was a very brief introduction to how Falco has been implemented. Now we will see how it works. There are a few things that you must keep in mind. We have, okay, so here I have my Ixcube icon. Let me drag it because I have a few screens, I go crazy. Okay. So this is Rhino. I think all of you know Rhino. And here I have my Ixcube application. Now, you can run in two different ways. Now I will close both of them. Okay. We start Rhino. We start Rhino and we make a new job. So basically now we have started the application. We have started Rhino. And if you want to work with Falco, the first thing to call is this tool here, connect to Falco server. So when I click on this icon, the software, since Ixcube is not running, Falk, wait 1 second, I have to manage a few screens here. Let me see if it's running on the background. No, okay. So as soon as I click on connect to server, Rhino starts the Ixcube server that you see here. And you see it doesn't have an interface. Okay. So when you see the program in this mode here, the program has started without an interface. It's just working as a server. It's fine. You are able to work in Falco, and clearly we are not working inside Ixcube because it started as a server. This is one way that you can work. Another way, if you want, I close everything. I start Ixcube. It's a bit slow. There too many things are working. Okay. The computer is going a bit slow. I start Ixcube. Then I run a Rhino. Okay. And once we have Ixcube and Rhino running, if I click on connect to server, Rhino connects to this server here. So basically you have an interface and you can also see what's going on when we are modeling. Okay. So two different ways that you can start. You can start the Falco server, the Ixcube and Falco server. Okay. Let's go on. We have connected to the server. You can check that you are connected to the server, calling about, and you'll see here all the models that have been licensed, where you have the license. And clearly, again, here we can extend the license with different models. Now, let's learn how to set up a model inside Rhino with Falco. The first thing that we need to do always is open a template. So we recall general settings, this dialog box here. These are the general settings for Falco. And I think here you recognize that these are the templates of Ixcube. Okay, so we have to choose a template. Clearly, we can make new templates if we want. We can make all the templates that we want, and we load a template. Okay. Once we have loaded the template, we can go here into the data records. The data records are not really equal to the templates. We have data records for points. This is a data record for point objects. In this case, you see they're all fixed. All the degrees of freedom are fixed. Then we have data records for curves. You see that a data record it has a name, and then we have all the properties that we find inside Ixcube when we select an object. And what are these properties? We have the type of FEM entity, if it's a beam, a cable, or whatever it is, if it has a linear or a non-linear behavior, if it's stiff deformable or not, the seed has been he got the seed from the template, the pretension of the object if we are using cables, the rotation angle in degrees, and so on. So basically, all the properties of a single element are defined in this table here. Clearly, we can make new ones. We can clone this, for example, make a new one. I want to call it 88 pinned. If I want an 88 diameter object, but pinned on the both sides, so I can go to the end restraint and select pinned and pinned. Okay, so basically we can define all the properties of a curve or define it with this table here, with this record. Then we have mesh records. These are for surfaces, and you see here S275 is a steel, pre-constraint is a membrane, and again here we have all the properties that generally we apply to shell elements or to membrane elements. We have the number of warp and weft curves if we are making a force density model, and we have the pretension, the warp and the weft pretension if we are making an FDM model, and so on. We will see later again these details. What is important that you understand that you have three tables, one table for points, one table for curves, and another table for the surfaces for the meshes. And we can change all these parameters. We can make new ones and change whatever we want inside these tables. Okay. So we have defined the tables. Now let's go and see how to make a model. We'll make a very simple model to start and understand how it works. There's one thing that you must understand. We assign properties to layers, but if we make a hierarchy of layers, we just need to assign the properties to the top layer, and all the child layers will get the properties from the parent layers. Let's make an example. I will make a main layer called model. So this is my model. Then I will make a layer called cables, another one called beams, another one called poles, nodes, and let's make a new layer, and I will call it surface. So I have defined a number of layers, but these layers, I will drag and drop all of them under the main model layer. Okay, so we have one main layer, and all the other layers are childs of the main layer. Now that we have defined the layer structure, we can recall this tool here that's called build model params. Build model params, we define properties for the layers. You see, as soon as I open this panel, he shows again the layer that we have defined. We have all the layers here. What I want to do in this moment, I just want to assign properties to the top layer, to the model layer. So I will select you need to set it to be structural. If you don't choose the structural type, you cannot assign properties. And we will assign for points, I want that all the points that belong to the model are free. This means that you see all the sublayers of the model will have the nodes defined as free. Then we define, I will choose one profile here, 88mm profile, and then I will choose a pre-constrained Ferrari. Okay. Properties, you see that we have near each property, there is a button where we can override some properties. We will see this later. Basically, what we have done, we have just assigned it to the model layer properties for points, properties for curves, and properties for surfaces. What I want to do is I want to change the properties for the nodes. So I will go to the node layer, and when you choose structural, you're overriding the properties. That means that the node layer will not have properties coming from the model, but has its own set of properties. And I want to set the properties for the points to be fixed. Okay. We will see the others in a moment. Basically, this is all the work that you have to do, is to define your set of properties for the layers. Now, let's make a model right now. I will just start drawing some simple lines, and I will start drawing inside the pole layer. So I will draw a line. I will activate my grid snap. And a vertical line 10 meter. Okay. Then I will activate my beam, and I will draw an arch like this. This is in the beam layer. Then I will use, let's make a new layer here. I'll call it beam 2. And inside the layer beam 2, I will draw this line here. And from the middle point, this other line here. Okay. So you see, we are just drawing simple lines. Then I want to draw in the cable layer. I will draw a cable that goes from this point. I will use the near snap. Let's go to this point here. Okay. So basically, I am just drawing this. I am simulating to do a car park, a very simple object. Then in the node layer, I will draw a simple point. Remember, we have set the node layer to be restrained. So this point here will be a restrained point. Now I can select everything and make a copy. Let's make 6 meters, 10 meters. Copy. 10 meters. Okay. So made a copy. Now inside the beam layer, we will draw again a curve here and a curve here. Okay. And now I go into the surface layer, and we create a surface by edge curves. So this is my surface, and if I look at the properties, it's inside the surface layer. Fine. One important thing to keep in mind when we make surfaces, you see that I have a plot of the surface where I see the warp and the weft direction. These are parametric surfaces, and if you know how parametric surfaces work, they have a domain of UV curves. And that means basically that we have a direction, a U direction and a V direction, and we will use this direction to set warp and weft direction of the curves. Another thing that we should check is the direction of the curve. So we can go into analyze direction. In this case, my surface is pointing upwards, and this is what we want. So we have defined all the parameters of this object. Now we have different tools here. The first tool is build model. We can also run directly the analysis, but just to show you how it works, I want to build the model. So we recall build model, and you see the software parses everything and generates this model here. If I go into the layers and I hide all the layers, and we activate this plot here, this is a plot of the objects. You see that here we have all the geometric objects. If I go in shaded mode, we have all the objects. This is the FEM hierarchy. This layer here is the CAD, the NURBS curves and the NURBS surfaces that we have defined. Here, these are the FEM entities. These do not belong to Rhino in this moment. They belong to Ixcube. We are just plotting these objects inside the Rhino window. Clearly, what's important is if we look at these, we have options in the display. We have options to look at a few things. the most important thing is look at the purchased points. These are the purchased intersection points that the software has used to check intersection between the beams, the mesh, and so on. You see that he has detected this point here. And another thing that we can activate is the orientation of the elements. These are the orientation of the FEM entities. You see this line here. Let me zoom in. Okay, you see here, if in the geometry we can hide, for example, everything. I just want to see the beam layer, and you see that we have two red points. It means that from between the 2 points there has been a beam has been built, and the direction of the beam, these are the axes, the local axis of the beam. So always the red is the axis that goes from point to point, and then we have red, green, blue. Green is the Y, and blue is the Z axis. And this is important clearly when it comes to assign profiles to these objects. We want to know the direction of these axes, so we're able to define the profiles easily. If I go back now and I turn off the orientation and the purchased points, so the purchased points are the intersection points. You see here, oh, this was not so, this point is not connected. There's a mistake here. Maybe the distance is, I didn't make it so accurate. Anyway. Now, we have defined this object. I have just recalled the build tool. But we have the tool here, form find. So if I run the form finder, I am running the form finder, the stiff form finder. And you see that we have found the shape. So we have found the shape of the membrane. This is the stiff form finder. We can go inside the plots. And I want to see, after the form finding, for example, we have the option here, post-process. I want to see the membrane stresses. So I can open this one and say, let me see the membrane stresses. Here you go. You see that the stresses are all one. These are the warp stresses, and we can look at the web stresses, and even the web stresses are all one. So basically, we have done our form finding without need to go inside Ixcube to do it. The nice thing is you can use these tools as a double interface, because if I go and let you see what's happening in Ixcube your model is there. So if you want, you can just build the model and then go inside Ixcube to do all the other things like structural analysis and patterning. But basically, we can do everything from inside falko. Okay. Let's make another example to understand better how this works. Let's see if if I have done a good job and I want to run a global form finder, and that means I want that the steel starts working together with the membrane. How does this work? If we go back to the build model, remember that in the build model, we find all the parameters for defining the model. We can define loads, we can define linear load combinations, non-linear load combinations, buckling load combinations, and even seismic analysis for buildings. In this moment, I want to run a global form finder. To do a global form finder, clearly, we want that the stiff elements, the beams, behave as real beams. You see this option here. In the analysis and form finding tab, these are all the parameters that you find inside, generally inside Ixcube when we run a non-linear analysis. So we have them also here, the number of increments and iterations, and the tolerance for energy displacements and forces. And clearly we have also this flag here This flag says set stiff elements to be fixed. What does that mean? It means that all the beam elements that we have here, the edges of this membrane, are all beam entities, and the software has set them to be fixed. So we have just run a form finding over the membrane. The steel is not working. Now we want to see if the model works also with the steel. So I can check off this one. And once I have checked off this, we have activated the nonlinear form finder. So the only thing that we can do is run the form finder again. Now he's running the analysis. It seems it's working. Let's see. Clearly, this message box here will tell you if the analysis has worked or not. And that's it. Just parsed the model. Let's see what happened. So to look at the results, you always go under combination. You activate the form finding because we have only the form finding results. And for example, once you have activated the type of results you want to see, you go into post-process. And for example, I want to look at the reaction forces. So I activate reaction forces. Change the scale of these. Yeah, these are my reaction forces and these are my bending moments. So basically, we have run a global form finder. Let's give a look at, for example, at the axial forces for the beams. Here they are. So these are the axial forces in my beam here. These are minus 0.82 in the cables. It seems that these cables are not working. There should be a mistake there. You see that there's no force here. So it seems that these cables are not connected. So we made a mistake somewhere on these cables. Let's see what's happening. If I activate these cables, let's move it here to the middle. Mistake, sorry. Let's move it here to the middle. So, okay. Sometimes you could get confused because these lines, most of these lines, all the FEM lines, you can hide them by clicking here, hiding the FEM geometry, and you see only the Rhino geometry. Let's run the form finder again. Okay, so we can activate the geometry and we can activate the form finder and give a look at the forces. Yeah, now we have forces on the cables. Oh no, zero, almost nothing. I think because it's no, there's no self weight, there's only potential. Sorry, it's true. Clearly we are doing we are running a form finding, so only the protection of the membrane is active on the model in this moment. Okay, there's no load. Next time we will see how to make a structural analysis with the loads, how to apply loads and do all the rest. This is a very simple example. Let me save this and show you now how to make okay. How to do patterning. We'll make the patterning of this, and then we will do a conical shape using the first density method. If I want to pattern this object here, clearly we don't have the mesh. We can run the grasshopper. I don't know how many of you have ever seen a grasshopper, but at the end it's quite simple. It's not difficult, but the Grasshopper has a huge amount of features. So somebody may get scared in the beginning because it seems so a little bit difficult, full of features. But basically, to understand how Grasshopper works, you just have a bunch of tools, geometrical and analytical tools, but they all work in the same way. And just to give you an example, if I select, I put on the canvas one of these tools that is mathematical operations multiply, you have inputs. I would put two numbers. Okay, so you have an input. This is a black box that does some kind of operation on the input and generates an output. In this case, it's a simple multiplication between two numbers, and so it has generated the product of these two numbers. Grasshopper works in this way for all the entities, all the components that you have. Clearly, the problem is that there are hundreds of components, so initially somebody can get scared. There are so many that you can get lost. But the nice thing is that you do not need to learn all of them to use Grasshopper. For example, I use only those that I know how to use because they're quite simple. Vector operations, curve, surface operations, and you can do almost whatever you want. Let's give a look now. I want to pattern this surface. Now, remember, the mesh does not belong to Ixcube. This mesh, sorry, to Rhino. This mesh is inside the Ixcube server. So we can go here into the Ixcube as a big menu here, you see. And we can drag and drop on the canvas, get group list. The get group list, you see here, will give me, you can always use, in the beginning, I suggest always to put this panel here and drag the output of these entities into a panel, so you can understand what's inside, what's coming out from the component. Basically, you see here, these are the layers that we have pushed inside the server. The cables, the beams, the poles, the nodes, surface, and beam 2. Okay. What I want, clearly, I want to make the patterns, and the group that I am interested in is the surface group. Okay. I want only this group. This is a list of names. This one here is the full names. They're all the same because we don't have any. Yeah. What I want to get only the surface here. The surface object, the surface group is the tensor group, and I want to make the patterns for this group. So there is a tool in the set list to manage list of items. I just want one of these items. This is the list, and the item that I want is number 5. 0, 1, 2, 3, 4, number 4. So I set index number 4. And if I link, you see here, so this was a list of names. From this list of names, I just want the item at index 4, and this is my surface. Once I have the surface, we can recall another tool from the Ixcube panel, get group. The get group wants a name of a group, and when I update, he gives me the mesh. I will get the mesh component here. Here it is, and hide this. So you see the white lines. This is the mesh of my tensor. Okay. What we want to do? We want to slice. To make patterns, we need to define boundary edges. We need to define some curves that go from edge to edge. And then we want to generate geodesics over those edges. And out of these geodesics, we want to make panels. Okay. How can we do that? Well, the first thing that we need to understand, if we look at the model from top, clearly I want to split the domain in equal panels. So I need to know how big. I know how big it is because I have modeled it. But we want to define, we want to know how big this object is just looking at the mesh geometry. From the mesh geometry, we can go into the params and we can get the boundary box. So I got the bounding box of my mesh. You see it, here it is. This is my bounding box. The bounding box, clearly, I need to get the domain of the bounding box. And in Surface, there is a tool called deconstruct box. So if I put deconstruct box, it gives me, you see here, in the X, 0 to 10, in the Y, 0 to 9, and in the Z, 5 to 6.011. These are the dimensions of the box. We are interested in the X dimensions. So again, I want to split this. This is called the domain. I want to split the domain. I want to know the X minimum and the X maximum. So again, we have a tool in the mathematical toolbar, deconstruct domain. Here it is. So this is the domain. I want to know the X domain, which is the minimum and which is the maximum value. And if I put here a panel, the minimum is 0 and the maximum is 10. Okay, so basically we have the mean and the maximum numbers of this mesh. I think that's quite clear. Now, what we want to do, I want to generate a number of slicing planes, 2 or 3 slicing planes between these two numbers. Okay. How can we do that? Well, we can do it in many ways. The most simple way is to generate 2 points. You are following me. I'm going quite fast. I know, but I want to generate a point. And you can go here. You have in the vector components, point, construct a point. The first point, the X coordinate will be 0. And the second point will have a coordinate X of 10. These 2 points, I can just generate a line between these 2 points. And here it is. You see the line, it's on the ground here. We want to split this point now into a divide curve. I want to make, let's say, 5 panels. So I say 5 points. I want to split this curve in 5. And these are my 5 points. Okay. Now that we have the points, what we want to do, I want to generate planes. Clearly, the plane here is YZ planes, and 1 plane for each of these points. So I can use this plane to slice my mesh. That's quite clear, I think. So we can go again. We have the tool generate plane. In the vector, we have plane X, Y, Z plane. Y, Z plane wants just the origin, and these are my planes. Okay. Clearly, these planes, I don't want the first and the last plane because these are the edges of my membrane. I just want the 4 inner planes. These are my planes. You see, it's a list of planes. But we can go again into set. We can get a sublist of these planes. So I have a list of 1, 2, 3, 4, 5, 6 planes. I want only 4 of these planes. And the subdomain, that means the sublist. I want to construct the domain here. I want the domain, the planes that go from number 1 to number 4. I know this takes a little bit time doing all these tricky things, but clearly the nice thing about this procedure is that once you have defined the strategy, you can pattern almost anything using the same technique. Now we have here a list of planes. We have only 4 planes. I just want to detect the intersection of the plane with the boundary of my mesh, and I have finished it. And we can do this. We go into the mesh and we say mesh edges. Clearly I want only the boundary of my mesh. Let's get the mesh, and we have it here. I will use this tool here to recall my mesh. So this is my mesh, and what we want to do, the naked edges means edges with only one triangle, and those are the edges that I want. I want to join these edges in a single curve, and I have a polyline. This polyline here is the boundary of my my membrane, the outer boundary. What we want to do, we want to intersect these planes with the boundary of my membrane, and we go into the intersection, and we have intersect line plane, curve, line plane. So we can put line plane, curve plane, intersect physical, curve plane, curve plane, sorry, not line plane, because we have a curve, a boundary curve, and the list of planes. You see now that we have generated the intersection points on the boundary of the membrane. It seems, for those that have never used Grasshopper, maybe all this seems a bit long, but if you think about it, we are using very simple geometrical operations to do this, nothing that nobody is able to understand. Now I have a list of points. I have a list, really have a tree of 4 elements of 4 lists of 2 points each other. I just need to create a line between these two, and this is quite easy because I go into curve, create line from this point here. I need the first index, so I go to list item of these points, number 0, and then list item point number 1. Point number 1 and point number 0, and we have generated, you see here, four lines. I will flatten this. We have 4 lines. At the end of all this was just to detect these 4 lines. The nice thing is, if we go back and we see how we have built this, the number of points that we have generated. Let me correct this. This would be math -1. Because if I don't do this, it will not work. Okay. Let me hide everything here, so you can see it. These are the lines. We have done all this to generate these 4 lines. But if I go back here and we turn this, you can generate how many cutting curves that you want. Okay. And clearly, with a bit more complex and involved things, we can generate equal distance lines. But we are not finished. Now we want to generate the panels, And for doing this, we go in Ixcube. And you see that in Ixcube, under the patterning tool, there is a tool called Make Patterns. Make Patterns, if we look at the parameters that pattern wants, it wants a group name. And the group name, we have it from here. This is my group name. So I can get this group name here. Group name. I want to pattern this group. Here it is. And then he wants geodesic slices. So if you want to generate geodesic curves, you need to input lines that go from edge to edge, only lines, and the software will generate geodesic slices, and that's what we want. Clearly, we have the option to generate section slices. We can generate mesh slices if you want to make a hole in the mesh. And we can also generate edge offsets, welding offsets, and we can apply also compensation. We have input this. The last thing that we need to do, we go to Ixcube. Where is it? And we get a pattern reader here. Okay. So we can say update. And these are my panels. Let's hide it now and draw. I will hide these. So these are my panels. Hide these. Let's draw them a little bit better, and then we'll make an example. These are my curves. I will hide this. So these are my pattern curves. Here they are. These are my patches.
Not hear anything.
Yeah, who is with the music? Sorry. Who is listening to the music? Thank you. These are my patterns. These are my patches. And then we have, again, the system lines. Okay. And then we have all the details, all the nodes, the text. So for example, I can go in display a text tag 3D. And these are my system points, for example. These are the system points. And these are the system point planes. And then we have to input the size. These are the size for these system points. Apply. So these are the system points for applying the welding, and justify at the center. And then we have the information, the pattern information, info planes, this one here, and info text is this. And info text is this one, and justification top left. And these are my patterns. So we have all the patterns, the patches, and all the information, the name of the panels also. Now, basically, the nice thing about this is clearly if you have to do only one, you don't need to go here to lose all this time. But if you're patterning a quite large project with, let's say, 50 cushions, for example, You can make a strategy for patterning one of these cushions, only one at a time, and generate all of them in one shot. Text planes, this one here, and text names. Here it is. So these are the pattern names. So we have seen basically all this. I have worked inside Grasshopper, and yeah, I have used most of the Grasshopper features. What's interesting was using these two components, make patterns and read pattern file, because make patterns generates a Rhino file, and this other component will read the Rhino file and split it in all its components. Okay. So this was a nice overview. Clearly, I see that it's nearly 5 o'clock. We'll make just 5 minutes again. I will show you just another example. How to make a conical shape. I will start a new project. Let me close Grasshopper. Okay. We have seen in previous releases, it's very difficult to use the first density method, for the simple reason that the first density method doesn't use a mesh. Let's see how we can make it. I would just make this one here my model, and this one my surface, and this one here would be my edges. Again, I will drag and drop my surfaces and my edges over the model. I will recall load template. It doesn't matter what template you use. You can use even the NFDM or FDM. I will load the template. And now we want to define a conical shape, or even next time I will see you how to generate 100 conical shapes in one step. But now it's important that we understand the principle behind this. What I will do now, I will just draw the base, a basic shape here. Okay, hexagon, and then a vertical line. We will copy. I will copy this on top here, and I will scale it to be my conical ring. So I want to generate a conical shape between these two. Clearly, to do this, I will draw a line from here to here. Oops. I will draw a line from here to here, from here to here, and explode these into simple lines. And I will make a surface by edge curves. This one, that one, that one. So this is it's a planar surface. You must be careful. The surface have to be untrimmed surfaces. So this is an untrimmed surface. Now I will use the tool rotate and copy, and I will just copy this surface. Okay, around all the edges. Now, one thing we must keep track of, the warp on the weft. I told you in the beginning, I think so. I have set up that U and V are drawn red, green. So red is my U and V is V. So warp and weft. These surfaces, I will put these surfaces on the layer surface. Okay. And then the edges of the surfaces, I want boundary edges clearly. Boundary edges, I will put them on the edges. And also these edges on the top, I will put them on the edges. So we have just defined this kind of shape here with surfaces and edges of the surface. Let's recall now the model properties. The first thing that you see, we have the option FDM, use the first density method. So we activate this option. We want to use the first density method. And then in the model again, we choose the properties for these objects here and the surface we choose pre-constraint. Under the model, we go into the surface. We set it to structural, and I go in override. You see now that in the override, we have the properties, how many curves you want in the warp and how many curves you want in the weft. Basically, these are the options that we see when we use the tool generate mesh inside Ixcube. But the nice thing is that here you can change them outside and even later, so you can remesh it. I have just set those curves. Let's use the tool build model. And you see that this is my FDM mesh. If we turn back, let's be sure that we have set, we want the edges to be fixed, okay? Because I want the top and the bottom edges to be fixed. And we can just run the form finder. That's it. Let me hide here and this is my membrane. We can give a look at the activating the stresses. I want to see the principal stresses. There we are. And the second principal stresses and the volume stresses. Okay, so that was quite easy. You could go back if you want, and you can change properties. I go into the surface properties here, and I want to change the weft pretension to 3. Clearly, this pretension becomes the first density value when you're using FDM. And you just run the form finder. You see, I have increased these curves here, and so on. So it's 5 o'clock. Anybody has questions? No questions? Fine, everybody was. Are you still out there?
Yes, I have a question. Very, very clear all.
Tell me.
What about the trial version?
Yes. I have sent an email today where you can get the one without the dongle, the version without dongle.
Yes.
Yeah, in a few days we will distribute also that one there. At the moment, only the professional one has been built. So yeah, without dongle, I think a few days, and we will send an email that it's available.
Okay, thank you. So I can upgrade my version to 5 and then go with it with the dongle.
With the dongle, yeah. Actually, we have the version that uses the dongle. In a few days, we will distribute also the one without the dongle.
Okay.
In any case,
thank you very much.
You're welcome. Clearly, Falco is a new application, but I feel that if you open this hand here, you click on the hand. It's not for tensile structures, but it shows you. There are a lot of video tutorials here. You see here, beginner video tutorials, and how to make templates, and how to use Grasshopper to make a parametric one, and how to make even a bit more complex models. So once you have learned how to make these, you have learned almost everything. One thing that I didn't focus on, for example, that we have also a falco. a falko toolbar here. What does that mean? It means that basically we can generate a complete parametric model and run the form finding and the analysis without even drawing inside Rhino. Because most people, I mean, if you're making a simple model, it's nice to draw, change the drawing and get results. But if you know how to use Grasshopper, clearly you work once and then you generate a lot of different solutions. Okay. Anybody else has questions? No, nobody. This was clearly today. This was the first time looking at falko. So we just did a very simple demonstration with simple examples. Next time we will prepare something a little bit more involved. Okay. Is that a question or somebody is talking? Yeah. Yeah, I'm looking at the chat. What about NFDM with conical shapes? Does it work? Thanks, Jerry. NFDM with conical shapes. You can do NFDM with conical shapes, but where is the problem? NFDM tends to do minimal surfaces. So clearly what we have to do, if I hide here and unhide my model, we have to put inside the model these curves. If I put these curves in my model, I get this one. NFDM model needs these kind of edge cables to pull out the membrane. So if I change the properties of these and I put them inside the edges, I have to make a new layer. I need them to be cables. Okay, let me hide the surface. So this one and this one, they have to be cables. Let me close Grasshopper here. So inside the cable layer, I will draw other cables. Okay, so now we have the cables inside the membrane. Let's define the behavior. I don't want to use the force density method. Okay, and I want that my cable layer, I want it to be structural, and I want these to be 10mm cable, and it's form find deformable. I want the pretension, where is it? 10 kilonewton is a bit too much. Okay. And we can build the model, see how it goes. There it is, and run the form finder. That's it. So you see, when you use the NFDM method, if we do not put these cables inside the membrane will tend to collapse in the middle of the shape because he tends to do a minimal surface. So if you like these kind of things, you're free to do it. Let's give a look at the stresses. Membrane results. That's it. You see, the stress is nearly uniform. The nice thing that if we go to Ixcube, your membrane is inside Ixcube also. And another thing, even if you're using the version without interface, when you save the model from Rhino, when you say save as, and I call it the version.
Saya mau apa? Tak ada bodoh jen saya aku. Memang 86 ada gila.
Ide yang kembang.
With a large mesh with
Dia
hard
tambah
weft
46
orientation.
tadi dia kak.
46 tu. Kau fight siapa tumbang mana dia betul ni?
Pasal kopi tu pernah. Kenapa ni aku 12 tahu.
Warp weft orientations to different meshes. You can split. You see that here we are using warp and weft orientation on the surfaces. Yes, you can assign different warp and weft orientations, splitting a bigger membrane in different pieces and assigning for each piece a different warp and weft orientation. Okay. So I think for today, that's enough. No, 4, 5 e mezzo, mira che ora. Ah no, we have another 20 minutes. Anybody else has a question? Nobody has questions. Nice.
Hey, Jerry, this is Paul here.
Hi, Paul.
Taylor. Hi. So your objective is to basically gravitate away from the Ixcube interface and start using the potential of Rhino and Grasshopper?
More or less, yeah. I mean, you see that Falco, I mean, it's brand new software, but it's very simple because you have a double definition here. I have, in this moment, if I take off this one, this is a definition of my model in a high level geometrical and with high level geometrical entities. I am using NURBS curves, NURBS surfaces with applied properties. And then inside Ixcube, I have my FEM model. So basically, we can work inside the model at a higher level abstraction. We assign properties to this model, and you keep a model with a high level abstraction. It's very easy to modify the model, to get a new version of the model, and to have to check it for different purposes. And out of this higher definition model, you generate your final finite element model. You got it?
Yeah, I think so. So as Falco was written as like an interface by someone else, and you just plugged in your
No, we
Ixcube part?
developed Falco. Yeah.
You wrote Falco.
Yeah, we developed Falco.
Okay. As the means of dialoguing between Rhino and Ixcube.
Exactly.
Okay.
The concept is, I mean, I don't know, but if you look at some things, for example, they seem very stupid, but let's give a look at something very simple. I put myself in this layer here. Okay. And I draw some curves. Like this, and then we split these. Okay. Okay, so I'm making this object here with these curves, and then I can make a surface edge curves. Okay, so I have made a surface inside these curves. I will select, edit, select objects, curves. Where is it? Curves, and I will put them on the edges. Okay, and then I will just to make things a little bit, I will make a circle, and then I will trim. Okay, so I have built this kind of model here. Now, if I recall generate model. So basically, you see the finite element model has been generated out of that model.
Wow.
And you do not need to do anything. Clearly, here in the build parameters, you have all the parameters that the software is using. These parameters here, the curve tessellation length, the mesh tessellation, and all this stuff here that control the quality of the result. But I can run an analysis now of this object. So if I hide here, yeah, this is my finite element model. So, for example, I can use this. I can apply loads and get results out of this object. So clearly, what happens? This is my finite element model, and I have my definition is this one, and this is my CAD model. In my CAD model, I am using NURBS curves and NURBS surfaces, and these are converted to a finite element model by falko.
Okay. So the future, this is the future for you, for your
for me, yes. I
Yeah.
mean, once it gets, I think it's already quite stable. I mean, I've done quite complex things. I can show you this model here, for example. Videos.
And what version of Rhino do you need to run falko?
This is running 7 now, the last one.
It needs to be 7. It can't be earlier.
This is 7, yeah.
Okay. And which
So,
version of Grasshopper?
With the 7, you get the last version of Grasshopper.
Okay.
You see this one here. This is the dome, and out of the dome, built this model here. Yeah. So this is with all the properties, and if it still works, let me see. Maybe I have to load the. I don't have my the profile anymore here. I don't have the template I have used. Anyway, it doesn't matter. This dome has been built. This is steel dome built over a parametric dome inside Grasshopper, and out of this, we have generated the model and run analysis. And all this is the example here. So there's a video tutorial on this. And this is something that if you want to do it, modeling everything and splitting all those beams and all those curves into finite elements, clearly you can do it. But generally what happens that when you're doing a job like this, you generate 10, 15, 20 different models, because you make an analysis and then you understand that you have to change the model, you have to do something, and it takes a huge amount of time. So basically, if you have a system like this, you can change everything on the fly.
Yeah.
Got it.
Amazing. Yeah, really.
One question, Jerry.
Jerry, tell me.
Gap elements.
Gap elements.
In Ixcube, you put the magic code to simulate. Here, what is going on?
Yeah, no, it's not available yet. That one.
No, okay.
We will add it. We will add it later. But yeah.
Okay.
The gap element is not.
Understand. Okay.
Jerry, I had a question.
Tell me.
If I had, let us say, 20 different member sizes, so they would be in different layers, because I would have to assign each of them member sizes.
Sorry, your voice doesn't come. Can you tell me again?
So if I have different member sizes,
yes.
So they would be all in different layers.
Different layers, yes, different layers. You have no limit on how many layers you can generate. Okay, so clearly you put, the rule is on each layer you put the family of profiles that you want to use.
So we can assign families of profiles also?
Yes, we have also. I didn't show you, next time we will give a look. But here inside falko, we have the falko for Ixcube. Where is it? Here it is. And in the falko for Ixcube, we can select, you see, properties to apply to layers.
Okay.
You see here. So we can do this in a parametric fashion. So I can choose also this one, and that means that curve data. You see here, these are all the profiles available, and we can assign these profiles to layers, choosing them from a strategy. The strategy could be, today we are not going to show everything, but we can have here, for example, we can run a Grasshopper script when we run the analysis. And that means that I could run a script, I could generate the model, check results. One thing that I didn't show you, but we don't have so much time, we can check the results from here. So basically I can check the steel against Eurocodes and get back this data inside Rhino and inside Grasshopper. We could define families, and then I can make an optimization based on the safety factors. I can change things and change the model, but this is quite involved. Today we are just scratching over the surface to see how this falko works.
Great. Another question was, it would be possible also to do pneumatic form finding?
Yeah,
falko?
absolutely. Yeah, of course you can. I didn't show you, but here we can generate both from falko, but even from Ixcube, we can generate inflatables. So we can generate inflatables, and we can then define the chamber pressure for the inflatables, and then run the form finding. Next time I will show something a bit more complex. I have made a model, but clearly when you start making something complex, we have to work only on one model. Today was more showcase of what falko is and how it can be used together with Ixcube. The nice thing about falko is that you don't need to know Grasshopper if you want to use it. But if you learn Grasshopper, you get more power. But you can add Grasshopper slowly, step by step, to your normal workflow. And still, if you don't know how to use Rhino, you can generate a model, and you go back and you have your model in Ixcube. So you can continue working inside Ixcube if you're not so used to Rhino and Grasshopper. So you can get the best of all the worlds.
So last question was about Idea Statica. We would have that also, those kind of plugins also in falko, or will we doing this
at the moment? Yeah, no, at the moment you have it, but falko and Ixcube is the same thing. I mean, once you generate a model, if you run analysis inside Ixcube and you open the file from Ixcube, because the file is available when you work in falko, your file is available inside. If I go here to the directory, I was working in here, Ixcube. Where is it? Here, Ixcube 50. I don't find it anymore. Yeah, I was working inside this directory here. If I go, I think here. No, it was not this. I don't remember where I was working. Make things too fast. Anyway, when you save from here, you save file, save as. You save the Rhino file, and falko calls Ixcube to save also the Ixcube file. So both files are available when you come later. It means that you can just work in falko, and then you come here, you open the file, and you are ready. All the loads, all the members, and all the analysis that you have done are also available inside Ixcube. And about Idea Statica, yes, Idea Statica is a great tool for checking designing the connection nodes. So we are using it and we find it very, very powerful. But that's you just get it from the Idea Statica people. Hello? Is there anybody out there?
Here,
Yes,
here.
yes.
Well, the concept today was to show you about this falco. I don't know how many of you out there are using the Rhino and Grasshopper. I know there are some powerful power users, but you know, Grasshopper, I mean, somebody asked me to do ATFE cushion patterning for thousands of cushions. So you said, how can you make thousands of cushions manually? It's impossible. So using this tool, you're able to generate thousands of patterns in half an hour. And that's a huge amount of time and a huge amount of money if you think about it. Okay. Fine. So this was our first meeting, but we will have a lot of these meetings. If you want to join us in learning how to use all this stuff. And we will talk about the fluid flow analysis system. That's completely new inside the Ixcube. And I've got lost here. Here it is. So in the next lessons, we will give a look at the fluid flow analysis. We will give a look at the new patterning system. And yeah, we will make some examples using falco to make a bit more complex involved stuff. And you see here we have the fluid flow analysis integrated. Yeah, and we will talk about all these features. So the key idea is 1 hour and a half small lectures, so you don't get tired, and even I don't get tired, and we can discuss about all these features and even new features. If you want to see something new that is missing and we want to implement it, we can work on it. Okay. So that's it for today.
Thank you, Jerry.
If nobody has any more questions, thank you.
Thank you, Jerry.
See you. Thank you, Jerry.
See you next time.
Thanks, Jerry.
Thank you.
Jerry. Cheerio.
Thank
I've
you.
been waiting
Thank
for
you.
CFD for the CFD lecture.
Thanks, Jerry.
Thank you. Hi, Diego.
Hi.
Hi, Hector.
Thanks, Jerry. Thanks.
See you next time. Yeah, I think next week we will send another email for making another small session, and we'll see what kind of topic we want to discuss. I think the fluid flow analysis to show you how it works.
Yes, that will be great.
Yeah,
very good. The plugin for the wind tunnel also.
Yeah, that's the fluid flow analysis. Yes.
Yes. Okay.
Yeah,
thank you very much.
Yeah, maybe we can discuss about that one.
Okay.
So I suggest to give a try at Rhino and Grasshopper and learn a few things, because you will enjoy working with it, and you can do amazing things, and you'll see how much time you will save. Okay.
Okay.
Okay. See ya.
See you next time.
Okay.
Bye-bye.
Okay.
Bye-bye.
Bye-bye.
Bye.
Bye.
Bye. Bye. Bye.
Bye. Bye.